Hello, everyone. This is Alper Kerman. I'm the principal lead for Zero Trust Architectures project at NCCoE. Today, I also have my colleague, Bill Newhouse, who is the principal lead for Migration to Post-Quantum Cryptography project at NCCoE. Today, we're going to be briefing you about these two important projects at NCCoE. We both work for NCCoE, which is the National Cybersecurity Center of Excellence, which, by the way, is a component of NIST. So it's actually a part of a very well-known laboratory program at NIST, which is the Information Technology Laboratory, where NIST, conducts government research in IT and cybersecurity. At the National Cybersecurity Center of Excellence, we work with industry collaboratively to build cybersecurity solutions that are example cybersecurity solutions using commercially available technologies that are contributed by the participants on the project. Every project, that we envision about launching, and even the current projects that are ongoing right now at NCCoE has gone through phases. In order to initiate a project, we first have to define it, obviously, and to do that, we do market research, we do scope and impact analysis, and then we write up a project description. And then we publish it and solicit participants to participate on the project. And then once we have enough technologies on board, then we launch the project officially. And then project starts. Of course, we start with a design, and then we start building our solutions, so on and so forth. So that's sort of the engagement and process. Of course, while we're doing our lab work, we're also developing the main deliverable on the projects, which is a 1800 series document that I mentioned earlier, which we refer to as practice guide, which is the document that we share our findings and discoveries and how we put together the solution. So a little bit of a background. I'd like to let you know how we got pulled into Zero Trust efforts initially, which was in partnership with Federal CIO Council back in October of 2018 when we held a Zero Trust workshop, which is the event that actually led to launching a year-long project, a Zero Trust research project at NIST in early 2019. At the end of that project, we published the NIST Special Publication 800-207, which is our Zero Trust architecture guidance. And then we decided to provision a lab to build a Zero Trust test lab at NCCoE. So we did that. We put together a small-scale infrastructure. We got our hands on some Zero Trust technologies. And then we started conducting tests using the test cases that we developed for gap analysis, so on and so forth. That was overall fact-finding and educational experience for us. But it also paved the way to launching this current project that we're on now, in which we solicited participants in early 2021, and then launched this project in July of 2021. And obviously, since then, we've been at it until this point in time. Initially, we had to build a baseline environment that mimicked a typical enterprise environment, one with multiple clouds, coffee shop, branch office, and multiple on-prem environments with workloads, so on and so forth. So that was an initial phase. And then once we were done with that, we started building ZTA implementations over that infrastructure. So we've been doing that. We've been building a lot of different examples based on different types of deployment approaches, which I will describe in a little bit. But in the meantime, we've also been focusing on developing our practice guide, which is the 1800 series document that I mentioned in my agenda. And so we've been making preliminary draft releases of that as we, make discoveries and to share our findings on the project as early as possible. So this is a follow-on ZTA demonstration project for the NIST SP 800-207, the Zero Trust architecture guidance that we put out back in 2020, as I mentioned. More specifically, we're using the deployment approaches that we describe in that document. For example, enhanced identity governance, microsegmentation, software-defined perimeter to deploy example ZTAs, basically. And our demonstration scenarios are all about various types of users accessing resources throughout this hybrid environment. Because we have remote users, teleworkers, but you could be coming in as different types of users, such as employee versus contractor versus guest, to access the corporate and internet resources. There's also inter-server communication aspect of the demonstrations, cross-enterprise collaboration demonstration, trust score, confidence level with corporate resources, so on and so forth. So that's what the project has been about. This is our notional ZTA reference architecture, and it's purely based on capabilities that we needed to have in terms of orchestrating a ZTA. The very first couple of boxes to notice are the red boxes on each end of the diagram. One on the left, far left, is all about subjects. These are typically users, traditional devices, mobile devices, apps and services, laptops, printers, etc. On the resources side, of course, you have the apps, services, APIs, data, file shares, databases, storage, and of course they can be in cloud or on-prem. And of course, these resources need to be protected, so we need capabilities for that. And of course, everything throughout the any zero trust architecture environment needs to be obviously protected. So you need specific capabilities to do that. For example, you need ICAM capabilities, you need data security capabilities, security analytics capabilities, endpoint security capabilities, so on and so forth. Last but not least, you also need capabilities that can play the roles of policy enforcement as a policy engine, policy administrator, policy enforcement points, right? You need capabilities to bring those on board too. And so we had all of those on board to build a ZTA reference architecture. This is our physical demonstration architecture in the lab. At the bottom row, this is a very high-level architecture, obviously. And one thing to notice is the boxes, the silos at the bottom of the diagram, which is here, Enterprise 1, Enterprise 2, Enterprise 3, and Enterprise 4. The makeup of these environments are very similar in terms of capability, but we're using different blend of technologies to achieve that and building basically ZTAs over those environments. Outside of those environments, we have a coffee shop here, and then we have a branch office here. Branch offices associated with Enterprise 1. Mind you, this is a infrastructure that we built in the lab, and so it's provisioned behind the NCCoE network, which is provisioned behind our mother network, which is the NIST network. And so in order for us to enable multiple cloud environments in our lab was definitely a process. But we were able to do it. This is the main deliverable on the project, which is the NIST Special Publication 1800-35. This is a document that has 5 volumes: Volume A, Volume B, Volume C, Volume D, and Volume E. The shortest document is the Volume A, which is an executive summary, very high-level document, obviously. Volume B goes a little deeper in terms of approach, architecture, and security characteristics. And then Volume C is a much deeper dive where we, describe integration, configuration details, how we did them in order to demonstrate some of the use cases and scenarios that we scoped out on the project. Volume D is the functional demonstrations. Basically, it compiles all the use cases, more granular use cases and scenarios that we scoped out on the project. And so essentially, it's a demonstration playbook. Volume E is all about risk and compliance management. This is where we try to map the security capabilities that we build into our example ZTAs to previous guidance, such as CSF, 800-53, or even EO 14028. This is a list of our collaborating organizations on the project. Now I'll hand it over to my colleague, Bill Newhouse.
Great, thanks, Alper. Thanks for informing us about zero trust architectures here at the center. And as noted, I'll be taking us down the path of our project on migration to post-quantum cryptography. Essentially, we're trying to bring awareness to any of the issues involved with migrating to post-quantum cryptographic algorithms. And we're trying to ease the migration from the current public key algorithms that are deemed vulnerable to a quantum computer-based attack to new algorithms. And on the right side of this slide, we have 4 algorithms that have gone through several rounds of review with NIST and my colleagues in the NIST Computer Security Division leading a process to select the post-quantum cryptographic algorithms, and working with international partners, working with different groups who've submitted contestants essentially. And just last week, they published the draft FIPS 203 for Crystal's Kyber, which is a key encapsulation methodology. And then FIPS 204 is Crystal's dilithium for digital signatures. And then Sphinx Plus is another digital signature draft FIPS 205. So these final standards won't be out until next year. Right now, they're in draft form for about 90 days. And so we're in complement to a NIST PQC standardization effort that started in 2016, based on a couple of years and even maybe more than that of speculation and theory and science that says, hey, a quantum computer should be able to implement Shor's algorithm and break the mathematics of public key encryption, asymmetric encryption that we rely on. And as such, if we can break if this new quantum computer, when developed, and it doesn't exist today as best we know, but when it is developed, a lot of our asymmetric encryption, our public key encryption, will be vulnerable. So NIST started into this process because they knew it would take a long time to first identify the algorithms. And then second, all crypto migrations take a while. And this one is the largest one we've ever attempted. And we, meaning anybody who uses digital communications and wants to encrypt data and digital technologies. If you have cryptography, this is the biggest transition potentially that you'll experience, that anybody's ever experienced. And previous migrations have not quite been completed. In a moment, I'll describe some of our work streams and give you examples of that. But our goal here is to get people thinking about this space, to bring collaborators together, and to start to document activities that you can take depending on who you are. And I'll describe some of that as the next steps in this space. On this page and elsewhere in this briefing, you can use the QR code to get to the project webpage, the QR code to get to the NIST standardization of post-quantum cryptography, and to the paper that we use to describe the initial challenge. Alper described that all our projects start with a definition of a problem we want to work on together with industry. So moving here, we are, as noted, complementing a standardization effort in this same time frame recently, a year and a half ago. NSM-10 is a White House national security memorandum that says the U.S. needs to become, expert and continue to be an expert in quantum information sciences, and then the protection therein based on the potential of a crypto-analytically relevant quantum computer being designed. There are other agencies involved: CISA, the Cybersecurity and Infrastructure Security Agency at DHS, NSA, and essentially any organization that's part of the public key encryption use in the federal government cares about this space. So we're in support. Our work will be supporting those efforts, not in a perfectly direct way, but in a call out way. NSM-10 said you should have this project, and we do. So we're meeting the requests from the White House. There are a lot of challenges in adoption, implementation, deployment. That this is not uncomplicated. It is very complicated, and so what we can show will help smooth that out for many, we hope. I'll talk to you later. I'll list to you the collaborators that have joined us. We first announced the project in October of 2021, and then we spent, since then, we've been inviting collaborators to join us, and they respond to a Federal Register notice. They let us know they're interested through a letter of interest in the project, and then we offer them a CRADA, and those once signed, they become CRADA as a cooperative research and development agreement. They become part of the collaboration. The last three bullets in this slide here: coordinate with standard developing organizations and government and industry sectors. We are out communicating, visiting with all sorts of organizations all around the world or all around the country to describe what we're doing here. What I'm doing with you guys today is that. And the key one here for me is standard developing organizations. There are protocols that rely on public key encryption, such as TLS and QUIC, and there's also use of hardware security modules, HSMs, in cryptography, and the way the standards enable those protocols those protocols need to be updated. So they have vulnerable algorithms within them, and adding the new algorithms as they become standard will be a first step in the standard organization. So we're communicating in a two-way path. This isn't just us, saying stuff to them. It's listening as well and learning from them, and they learn from us. We have essentially established two work streams within this project, and the first one is to leverage automated tools to discover the use of quantum vulnerable cryptography. So Alper described that he has a laboratory environment for all of his zero trust architecture implementations, and he's created different realistic and scenarios. In our place, we are putting these tools onto our lab environment so that they can run as expected. Some of them will look at network traffic. Some of them will look at network traffic captures, PCAP files. Some of them are going to be more in the area of static and binary analysis of applications. And some are going to be able to scan inside tools that are being used for continuous integration and continuous development. I'll have a visualization to reinforce that, but we are going to be showing off these discovery tools, not to say one is better than the other, but to show you how they work, what they do, and what they give you back as an answer when you ask the discovery tool, what kind of cryptographic algorithms am I using? It's pretty well believed that most organizations don't have a full grasp of all the cryptographic algorithms they rely on. And so these tools are going to open your eyes in a lot of ways and help you prepare. As Alper described, this knowing what cryptography you're using could also be a policy enforcement decision in the zero trust architecture. The last bullet says we're going to be performing, and we are performing, interoperability and performance demonstrations. And those are some of the protocols and areas of use with public key encryption, certificates, and the hardware security modules, as I mentioned, that we have our vendors doing individual tests against the draft post-quantum algorithms that NIST is selecting to see what happens and what are the trade-offs, learn what it's going to cost us in computation and time and hardware and memory as we go through that. The areas that I described where discovery needs to happen on the left side of this picture in your code development pipeline is a good place to look. That's a different audience than inside your operational networks and services and protocols. So what do you see in network traffic? What do you see when you capture network traffic that you can then run a tool in to look at cryptography and the algorithms therein? And then operational systems and applications. Where do they make calls back to certificates and other HSMs and other things that will be needing to be modernized and updated to allow the new algorithms to function? To the right is the important part of once you have that data, you've got to normalize it, correlate it, use it, put it into a risk engine, which is the box that's the second one with a criticality of data kind of below it, in the sense that all of this is related to, I want to know what I'm doing, but what data is being protected is a big question, and there's no value to the sizes of these boxes. The words just fit inside them. Criticality of data, what are you protecting? What are your high value assets? And you put that in and you get a outcomes of prioritization list. We have not demonstrated that. We aim to demonstrate that in our lab so that you can get an example of the challenges to do that. And finally, we do have a project webpage that you can come join us. There's a place to sign up to get updates about our project and know what we're doing and be invited to any public events that we hold. So I hope this gave you a little flavor. Quantum readiness is the goal here. A quantum cryptographically relevant quantum computer will break public key encryption. Quantum readiness is that you've identified where such a device could cause you problems. There's a thought that people are storing and collecting data today to break later once that CRQC is available. And we are showing you the techniques to put these new algorithms in place, in use, and also to know what's going on with algorithm use that you have in your environment today. So really appreciate the opportunity to talk with you guys, and look forward to hearing from you if you're interested in these projects as we move forward. Thank you.